curious before we start class as to whether or not there was something additional that you guys needed to ask about homework that we didn't cover. You guys felt good? It was all right? Covered as much as you needed? You skipped a what?
Question. Yeah. There were so many.
Oh, because you guys were good and it was all right? Okay, cool. So I haven't read her like write-ups on the classes, so I didn't know.
Just a comment. The mic thingy, like the mic was going on and off, so I was kind of like.
Yeah, no, thank you. It was well, you guys could tell. I don't know if anybody's actually watched any videos from this year. The ones from this year are very muted in the sense of like it's on this little hover cam, and I'm over here, and yeah, it's quiet. You have to turn the sound up. So the nice thing of my microphone last year is that it was like a little lapel one, so it was a lot louder. You guys probably noticed, like the sound was really good, but then the wireless Bluetooth, whatever. It was Bluetooth. Reception would go in and out. So, and it died on me, which it doesn't even work anymore. But, so it's one of those trying to figure out the best way of doing things. I think we might be getting new boards next year, and they might come with microphones in them. Kind of like your computers have microphones built in, but we'll see. It's a big budget. Huh? Actually, I have a new one, but yeah, some of our teachers have the old ones. I kind of killed my time card. What does his do? Is it like flicker or how does it do?
The past year, like this Monday and last Monday, was the first time.
We're good on this. Okay. You guys were supposed to be working on section 4.67, starting it over the weekend, so I don't know how it went, but for us to go look at homework and where you guys stuck right now might not help everyone. So instead, let's get to our notes. And let's talk about theoretically what you covered in the video on Friday. Did you guys make it all the way through? I mean, if you skipped questions, you should have.
We made it to the video. You didn't.
Like it ended like right there. Like when
okay.
Sketch the graph.
Okay. So I think I probably copy and pasted, like I saw where it was headed, and so I might have accidentally copy and pasted too much. But let's go ahead and start here then. So you guys were just starting to write about tangent? Is that what was going on?
So we just did it so far with sketch the graph.
Got it. So we have the basic tangent. It looks a lot like a cubic function, except instead cubics go on forever, like negative infinity to infinity, one cubic curve. Tangents get broken up and repeat, and they have these little asymptotes in between, which we should know from the unit circle. Do I still have it up here? I don't. I had period 3's like cheater chart up here. Because tangent is undefined when it's sine over cosine 1 over 0 at pi over 2, which matches up with the graph. Tangent gets bigger and bigger and bigger from square root of 3 over 3, 1 square root of 3. That would be here and here and here, and then it would be in negative. Let's see, that would be the fourth quadrant. So first quadrant, it's like, yay, I'm going up, and then it's like, undefined, and then it goes, I'm going down. Negatives in the fourth quadrant. This is negative pi over 2 and then the unit circle. Negative 90 degrees to positive 90 degrees, but long story short, if you kind of have an idea of a normal tangent, now we have to start transforming him. Yeah. Okay, so transforming him. He's not quite as nice as sines and cosines. Cosecants and secants are easy cheesy. You get a sine cosine and you bounce off. We'll see that at the very end of class today. But for tangents and cotangents, they're their own little dude. They're separate. They use sines over cosines, but for their graphs, it's going to be a lot easier to say, let's find the vertical asymptotes like we do with rational functions. Let's find the vertical asymptotes. Let's get them in there. Let's find the horizontal asymptotes. That's what we did in chapter 2, but for tangent, we can't really do that because it doesn't have any horizontal. So to find the verticals, we say you, who's gotten all mixed up with like a dilation and a translation and whatever. Whoever you are, set equal to pi over 2 plus pi n. And then I can find all the different vertical asymptotes and mark them on the graph. And then if there was a vertical shift, if there was a D, then this middle point would have to move up or down to whatever that new height is. But usually there's not really vertical shifts of tangents. Usually they're still on the axis. They just kind of get moved back and forth. So wherever we find our vertical asymptote, we can always find the zeros. They're going to be halfway in between each of those vertical asymptotes. And so we got down here to this guy. Now, to be honest, this guy doesn't change much, right, guys?
Yes.
All he has is a divided by 2 on the inside. Inside means horizontal, right?
Yes.
It's a horizontal, shrink, because it has a 1/2. Stretch, because the inside is always backwards, what I think. So I need everything to double by 2, horizontally double by 2. So what do you notice about what happened to the asymptotes?
They got what?
They should have been here, now they're twice as far away. Does that make sense? So pi over 2 times 2, negative pi over 2 times 2. Look. And then check it. What's the distance between negative pi and pi? 1 pi and 1 pi is 2 pi. So then all I have to do is add 2 pi again. So pi plus 2 pi is 3 pi. And then I could subtract 2 pi. Oh, well, I only got halfway. I didn't keep on writing, but this would have been negative 3 pi. So the nice thing is, if you can figure out the first asymptotes, then all I have to do is say, what's the distance? And then that's my period. Let's just keep repeating. You don't necessarily have to have all those formula things memorized like you did for sines and cosines. And your waves. Okay. So, maybe some of you guys are getting your example down. I just showed the long way of doing it. Like if this had been a harder example, you take that little argument, set it equal to pi over 2 plus pi n, move that 2 on the other side. So then now I'm going to start at pi and shift by 2 pi's. So start at pi, shift by 2 pi's that way and this way, however many ways, however many cycles you need to show. And then the zeros, we can just take that same argument and set equal to 0. So, as far as the solving procedures, take the argument equal to pi over 2 for the vertical asymptote and equal to 0 for the zeros. Then the period, you could technically find it by making a little equation, setting it equal to pi, which is the normal period of tangent, half of the normal period of everybody else. Or you could just figure out the distance between asymptotes and say, oh, that's it. But cotangent, okay. What's different with them? Careful. He's the reciprocal, right? He's the reciprocal of tangent, which means he's also cosine, the quotient property over sine. Or adjacent over opposite. And so instead of cotangent being undefined at every pi over 2, every 90 and 270, or pi over 2 and 3 pi over 2, because he's the reciprocal, he's going to be undefined at the other places, aka the zeros and the 180s, the zeros and the pi's. And so his vertical asymptote, instead of being set equal to pi over 2, I need his vertical asymptotes to be at every pi. Technically 0 plus pi n, but whatevs. 0 plus anything is itself. So every pi, he's going to be in trouble. His period is just like tangent. It's going to be pi also. His domain range, his domain is still all real numbers. If he's like tangent, the whole like going down forever, up forever, just been flipped, quite literally. Range, wait a minute. I just put down and up. Isn't that a range answer? My bad. Down and up is a range answer. Domain, well, he just can't be at his vertical asymptotes. He just can't be at those pi ends. And then symmetry, does he have symmetry? Yeah, he's even. Because this is what he looks like. He's going to have asymptotes here. It's like he shifts from tangent. And he's the reciprocal. By being the reciprocal, his vertical asymptotes shift and his graph switches too. Some people, being tan is a positive thing. Sure, why not? So it's always going up. Being cotan is not, so you go down. I don't know.
Being tan.
Have fun with the little people. Third graders? Fifth graders. Oh, fifth graders. Oh, do you teach little people science?
Wait, here?
I think fifth graders probably figuring lessons. They go on North Campus once a month. And some of the higher science kids go and teach the little ones.
He and the struggle.
They do like a lab with them and they try to teach them to answer questions.
Oh yeah, we saw her sale today. Ooh, that new thing called like the SS.
The SS chemistry.
Yeah, that was so weird.
Party Uber.
I said they call it Joe.
We're supposed to have fun.
No, it was fun, but some people have a lame name.
Where?
The answer, his name is Joe. Joe the shit.
In the name comes back when you do the shit, so when you do the shit, and then she got all mad at me for saying the shit, and I didn't say the shit.
So, what if the cotangent gets all mixed up? What if the cotangent gets all transformed? P.S. You guys have corrections, right? It's a thing you're supposed to do. We'll take like 5 minutes beginning of class tomorrow. You guys can powwow if you need it. Sound good?
Ew, you're trash.
And P.S. If some of you are like, that last test, not good, you get tutoring hours by it. If it went badly, truly, you could get tutoring hours by being tutored by another honors pre-calc kid helping you with your corrections.
Emily.
FaceTiming tonight. FaceTime. Okay, anyway, it's an idea. Coming back, or coming in during math lab and getting like face-to-face. I don't know if you need off-campus, on-campus, whatever hours, but it's an idea. Okay, so we're transforming cotangent now. Vertical asymptotes, no big deal. Just take that bx minus c and say you're not allowed to be pi n. Tangent's not allowed to be pi over 2 plus pi n. Cotangent, well, he just starts at 0, so 0 plus pi n. Sweet. Finding zeros, halfway between the vertical asymptotes. It really is the easiest way, but if you want a way to show it, you can also just take that argument, the argument right here, and set equal to 0. And then you could do your little plus pi n. Because we know it repeats and repeats and repeats. This technically would repeat this direction. Goofs, what are you doing back there? There we go. Yeah. Good try. And the period. You could just take this guy and set it equal to. Can I do that? I probably shouldn't. Better way of doing that. I know. I made a mistake. Happens all the time. The normal period for cotangent is like tangent is pi. We have a horizontal dilation by a factor of 1 over b. Remember, not what you think. Flip, flip, flip. So we could find the period by just saying p is equal to its normal period divided by b, or 1 over b times its normal period. The period formula doesn't change at all. Just the normal period for tangent and cotangent is pi instead of your waves, which is 2 pi. So,
Can you read the find zeros, please?
find zeros. Oh, halfway between.
Oh, okay.
I just
That's what we're trying to figure out. We're trying to do that.
between vertical asymptotes.
What?
Bx minus b equals 0 plus pi n. It's a little cotermination.
Vert?
Just the zeros. And then remember, everything's pi apart. Because the asymptotes are pi apart, a normal one, a non-transformed one, and then the zeros are pi apart also. Everything's pi apart. So, this guy. I have an example. Can you guys see him? He's 2 times cotangent of x over 3. That's okay. I think we can see him. So we're going to start with vertical asymptotes. We would take our x over 3. We would set it equal to pi n. So what does that give us? Technically not equal to, not allowed to be there, but we're going to put the dotted line at those locations. Yeah, multiply both sides by 3. And don't you just get that x can't be 3 pi n? Are we okay figuring out what that means? Who are n's again?
Numbers.
Yeah, what kind of numbers? Z, or you can think of it like a little squished I. Integers! Oh, integers. Positives and negatives. But only whole number positives and negatives. So, if you plug in 0, oh, it's 0. Okay. Because there was no horizontal shift, it's going to have that 0. But then plug in 1. Well, where's the next vertical asymptote? Stink. It's like pi and 2 pi and 3 pi. It's all the way out here. Do you see it? Plug in 1. Plug in negative 1. Uh-oh. Negative 1, negative 2, negative 3. Dang, it's all that here. Did this thing get horizontally stretched? Yeah, it got tripled. It got tripled. Horizontally stretched?
So if you're vertically stretched, I'm vertically stretched.
You goof. Hey, where's the 0? We found the vertical asymptotes. Where are the zeros? 1.5 pi. What did Emily do? She did this one halfway between. She's like, whatever. It's 3 pi and it's 0. It's right there. And she did like the little problem solving, discovery, experimental. Oh, I know that. And then I'll just, yeah, cool, halfway. And she's totally right. It's going to be 1.5 pi. Or another way of saying that would be 3 over 2 pi, right? Or 3 pi over 2. So this would be negative. But there is a way to solve for it. I technically gave a little baby formula, so if you want to, you could have done x over 3 is equal to 0. Oh, my bad. Guys, 0 is the placement of the normal cotangent's vertical asymptote, right? Where's its first 0? Hold on, my formula's wrong. Someone help me fix my formula, please. This one's wrong. 0 is a location of an asymptote. I put this underneath zeros. What should I have set this equal to? Where's the first 0 of cotangent? Do you see it? The zeros of cotan are pi over 2.
Oh.
Pi over 2 is the 0. Struggle. I guess that makes a little more sense. Because otherwise we would have gotten 0. We're like, wait, there's a vertical asymptote there. That can't be a vertical asymptote and a 0. So we solve. We multiply. Oh, we multiply by 3 pi, right, Sophia? Done. So what did you do Emily's way, which is my way, which is just, I mean, I agree with her. Like, my brain thinks like that too. If you find your asymptotes, it's just halfway. Easy. You can average them if you want. 0 plus 3 pi divided by 2. Or you can say, I know where the first one is. The original 0 is pi over 2, so when will you be that? And if you want, you could also do your little plus pi n, which would be plus 3 pi n.
I'm
Not back any further, though. We start to get dangerous.
What else could I do?
You missed it up something right there.
No.
What? Let's just call it.
Jeez, look at his desk.
Yeah, I've been
He has
sitting
long
around
legs.
He
Okay? He has long legs.
Really not at all.
Neither you have long legs.
Here's the question. How did your desk get on top of his desk, though?
Exactly.
I tried to move it back and it slipped back.
Oh.
His 4 legs are not all on the ground.
My legs are flooding right now.
His 4 legs.
All right. Reposition desk. The point has been received from here and from there.
Forward, you boomer.
Forward.
Forward. Look how much space you have.
Yeah, you're gonna have to come up to where your khaki is. That's technically where it's.
Dude, don't kick.
There we go.
This is all starting because you have,
All right. Calm thyself. Although technically the desk is over there. But I know. Okay, so we need to go to cosecant and secant, and it's gonna be really easy. But I want to answer Priyanka's question. So let's focus on something productive. Go ahead.
I'm just confused. I'm sorry.
No. Oh, I didn't finish my swoop. I'm so sorry. Was it? Oh no.
I was like, when, so the VA, if x is not equal to 3 pi.
Well, when the original just plain old, if there's only an x, but if the argument changes, the vertical asymptotes occur whenever that argument is pi. So what I did is I took whatever this guy's argument was, which was x over 3, and I said, you're not allowed to end up being pi. Because if that ends up being pi, then this will end up being pi.
Okay, so how do you, like, how from that did you determine where to put your.
Because, well, I said it in words, but I can show it this way too. Remember, n are integers, so integers mean all of the negative and positive counting numbers. So what I did is I started at 0, plugged in 1. I could keep on plugging in and get however many asymptotes I need.
So the vertical asymptote in the middle is the one where you put in 0.
Yes.
And then.
Well, where I set equal to 0.
Okay.
That makes sense.
And the zeros? It's the same thing.
Well, yeah, except on the original graph, the zeros don't, and that was my bad. I said equals 0, but that's what's going on up here, 0 plus pi n. Down here, the 0 of the original cotangent is at pi over 2 or 90 degrees. So I say, hey, when will you be where, when will the cotangent of you be at pi over 2? Is ultimately. And then I'm solving that. Nice thing is, if we have a little bit extra time, I'm not sure we will with all of the extra. You people. I could do maybe another complicated example, or a more complicated example. But wait, guys, I haven't drawn my swoops yet. Is there going to be any difference in the swoop, or do I just like, swoop, there it is, then? Wait, why am I going down?
Because it's a plus one.
Yeah. Well, because cotan is a flip a tan, and you're positive, or you're like, yay, you're getting tan, but then cotan, you're going the other way. But isn't there something else we haven't dealt with yet?
Hey.
We haven't talked about the vertical stretch. Vertical stretch. I don't know what's the big deal. Vertical stretch.
Skinny.
We haven't talked really about how high or how low tangent goes, besides the fact, and cotangent. Besides the fact that we've mentioned it goes forever high, forever low. So how on earth do we do a vertical stretch if it's just forever high, forever low? It's not like the waves where we change the highest point because the highest is infinity. It's not like the waves where we change the lowest point because the lowest point is negative infinity. Huh? In the cheater chart, where, for what angle, is the nicest, simplest value of tangent?
1.
1 is the value, and it happens at
90 degrees.
pi over 4, because that's where the
45.
isosceles triangle is, where x and y are both root 2 over 2's. Root 2 over 2 over root 2 over 2 is 1. So pi over 4, 1. Good. Okay. So, I know at pi over 4, if tangent's 1, what else is 1?
Y.
Cotangent. Because reciprocal of 1 is
1.
So I know pi over 4 is going to have a 1. What does that mean? If I go halfway in between my vertical asymptotes, there's a 0. If I go halfway in between that and the vertical asymptote, it's the 1. Wait. If I went halfway between 3 pi and 0, okay. If I go halfway again, isn't that going to be some awkward, like 3 pi over 4, because a half is a half? So 3 pi over 4. Yeah, there, and then good. So 3 pi over 4. But why is this not going to 1?
Because it's a 3 stretch.
Not because of the 3 pi. That is proportionally accurate as far as halfway to a 0 and then halfway to the 1. But it's going to instead be at a 2 because of the vertical stretch. So the way that you could make this at least somewhat accurate is to go halfway again to 3 pi over 4. And you could mark the other one. It would be, let's see, 3 pi over 4, 6 pi over 4, 9 pi over 4 if I was counting by 3 pi over 4s. And then I would need to go to negative 2. That's one way of showing that vertical stretch. But do you guys see how we're still going to be just swooping there it is? So to some extent. I'm not going to make a big deal with vertical stretches or shrinks on tangents or cotangents, except for the fact that if you were to draw a swoop like this, it better be super stretched. And if you were to draw a swoop like this, it better be super shrunk. Otherwise, if you just kind of do like a normal swoop, there it is, it'll probably be okay. If you want to be super, super safe, you could go ahead and do this extra point where pi over 4 would hit at 1. Or where 3 pi over 4 would hit at negative 1. That way you could very clearly show me the vertical stretches and shrinks. Sorry, that should be on the curve. There you go. That is a way to be like, hey, swoop, there it is. Oh, swoop, there it is. To make it very precise. But to be honest, as long as you kind of show me like, oh, okay, it's swooping and it's a little bit stretched, like I won't totally mind. And I love that you have the zeros and the asymptotes and the correct direction of the graph. That's probably enough for me. Now, sines and cosines, and I'm very specific about how high, how low, each of the waves, you gotta have those 5 key points. For tangents and cotangents, the zeros, over here. The zeros, the vertical asymptotes, the correct distances, and then the right swoop. The right swoop. Now, cosecants and secants. Whoa! We did like 2 pages each. 2 for cotangent, 2 for tangent. Like, you're really gonna squish this into 1 page? Yep. Because they're super similar in how they behave. Now, there are the transformed ones over there. Yeah. But why, oh why, am I going to squish this all in one page? Well, first of all, green pen is review. Almost always. Green pen. Oh, look, it's review. Green pen is review. Whose graph? As you guys are writing, you have to think about this anyway. Whose graph, or which other trig function whose graph we've already done has something to do with cosecant?
Sorry.
Exactly, because cosecant is the same thing as 1 over sine of theta, right? And the whole reason he can be undefined is because sine can be 0. And if sine can be 0, then cosecant can be 1 over 0, which is undefined. So when is sine 0? Some of you were like, unit circle 1, 2, 3, 0 is before the 1, so it's 0. For others of you, if you remember what sine looks like, well, actually, you know what? I'm going to put sine down here. It's going to be really helpful in a second anyway. There's pi. Sine starts in the middle, and then it goes up, and then it goes down, and then it goes down, and then it goes up. Isn't this the sine curve, guys? Where is sine 0? Oh, 0. Where else? Pi. Where else? 2 pi. If you learn the sine curve, maybe you don't have to go to the unit circle to think of when sine is 0. Like, oh, sine 0 there, and there, and there, and there, and there, and there. Where's sine 1? Oh, boop, boop, at pi over 2. Where's sine negative 1? Oh, boop, boop, 3 pi over 2. Okay, but long story short, sine is 0 at 0, pi, 2 pi. Wow, I could write this forever. Oh, that's why she does the pi n thing. It could be at this one, or 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 this one. Okay, keep on going forever. I'm going to go ahead and get my negative pi, negative 2 pi. Negative pi over 2, negative 3 pi over 2. If I follow my wave, it's going to be down, and then middle, and then up, and then middle. Okay, I'm in a little sine curve. She's drawing a sine curve where there's supposed to be a cosecant graph. I think they might work together some. So right now, we know that cosecant is going to have asymptotes at this guy, and this guy, and this guy, and this guy. Hey, do you guys see how cosecant is having asymptotes anytime sine hits the axis? You see it? I think that's a graphing trick. Okay, where is secant undefined? Okay, who's secant? He's related to what other trig function? Cosine. That was close. Cosine. I brought this up because you could think of unit circle like 1, 0, 0, 1, negative 1, 0, 0, negative 1. When are the sines and cosines 0? You could think of it that way. But if you know cosine's graph, couldn't you? Let's see, 2 pi, pi over 2, 3 pi over 2. Shouldn't you know that it hits 0 at the pi over 2's? It's not there. It's, oh, pi over 2. And then at negative pi, sorry, at pi it's negative 1. At 3 pi over 2 it's 0 again. And it's back there at 1. And then it does that on the other side too. And there's your negative 2 pi. Ooh. Sorry, a little messy. So, pi over 2, right? It's not 2 pi, it's not pi, it's halfway. It's boom, there we go, pi over 2, and boom, 3 pi over 2. So at pi over 2, and 3 pi over 2, and 5 pi over 2, and oh, that's why she does the whole pi over 2 plus pi n, because it's going to keep on repeating and repeating and repeating and repeating both directions. Okay, so secant is going to have vertical asymptotes at all of those places. There's one. There's one. And how am I finding these places? The intercepts of the sine or cosine. And what else is going on? Why am I saying the cosecant and secant curves bounce off their reciprocals? Maybe it's, oh yeah. Because why? Oh yeah. They're going to be parabolas. Maybe some of you guys remember from last year. And their reciprocals, 1 over. So What's like, that's kind of a hard question to answer. What's the highest sine and cosine go?
1.
What's 1 over 1? Oh, that's weird. At the highest points, they're going to be the exact same thing, because when sine is 1, cosecant's 1. When sine is 1, cosecant's 1. How about the lowest points? -1. What's 1 over -1? Oh, that's weird. It's like they match up at all the max and mins, all the peaks and the valleys. Or if that's the same for cosine. 1 over 1. Oh, yeah. 1 over -1. 1 over 1. 1 over -1. If I flip all the 1s and -1s, it's the same thing. But what if I was to flip, now here's an awkward one, but the nicest other value of sine and cosine, we've dealt with the zeros, we've dealt with the 1s and -1s. I mean, ew, root 2 over 2, no thank you, root 3 over 2, 1/2, okay. 1/2 happens for sine at pi over 6, right here. A little bit past the vertical asymptote. So, question, what happens if you flip 1/2?
2.
Yeah. So where sine is a little bit lower than 1, cosecant is actually going to be like up here somewhere. Yep. And if sine is 1/2, oh, it's 2. If sine is -1/2, oh, it's -2. And -1/2 is -2. Now, there are all these weird decimals in between, flipping root 2 over 2 and flipping root 3 over 2. But as soon as we get a pattern, we can just follow it. Because, guys, check it. It has to go to its vertical asymptotes. It has to be flipping off of the sine. Flipping as in bouncing, as in taking the reciprocal of. So guess what secant's going to do also? Bounce, bounce, bounce. So why? If sine and cosine are here in all the values in between -1 and 1, why are cosecant and secant outside? Because they're the reciprocals. They're going to match up at the 1s and the -1s, the maximums and the minimums, but everywhere else, they're taking the 1 over, or they're flipping, or they're taking the reciprocal of those values. What was little is going to flip to be big. And what was little negative is going to be flipped to be really negative. So how on earth are we supposed to, wait. Shouldn't these be way harder? Because sine and cosine, we talk about D and A and B and C over B and like all of the different key points. Why did I literally just write graph the reciprocal function first? What else do we do? Yeah. So who is cosecant, the reciprocal of? Ah. Does that make sense? He's the cofunction, you're right, he's the cofunction of secant, but he's the reciprocal of sine. So guess what we're going to graph? The reciprocal first. We're going to graph y equals 0 plus 2 sine of x. Why did I put a 0 plus? There's no vertical shift. Technically the letter's D, but yeah, there's no vertical shift. Do you see why I was double checking you had no questions on section 4.5? Because the graph cosecants and secants, what do you have to be able to graph? Sine and cosine. But if you can graph sine and cosine, check it. So we're going to go up 2, and then we're going to go down 2, and then, wait a minute, I have a shift. Where's the sine gone? Yeah, he's gone left pi over 4, so he's going to start at negative pi over 4, 0. But it's 0 because he didn't shift anywhere, so he's still on the axis starting. He's going to go left pi over 4. Wait a minute, and what's his period? How do you know that, Sophia? But you're totally right. There's no coefficient in front. There's no b technically, but yeah. So it's understood 1. So I need to start at pi over 4 and go, is it okay if I make this 8 pi over 4? Because if I'm counting by fourths, I really want to know who he is this way. It's a lot easier. So I'm going to go negative pi over 4, and then I'm going to have to go, let's see, 1, 2, 3, 4, 5, 6, 7. Why did I stop at 7 pi over 4?
Because that's where the period starts.
Yeah, if I start at a negative, I'm going to have 1 and then 7 more to be my whole shabam. Wait a minute. Ew. Aren't I supposed to, like, go a quarter of the way? What would a quarter cycle be? 2 pi cut into fourths. Oh, two of those little, pi over 2 or 2 pi over 4, two of those little tick marks. So I'm going to go 1, 2, I'm going to be up here at 2 because he got stretched. And I'm going to go 2 more, middle, 2 more, down to -2, and then 2 more. Okay. Whew, was there a lot of math just getting this done? It could have been worse. You had worse ones in homework, whatever it was, 27. You had worse ones in that homework, I'm sure, but it took some time. Why am I still just making him dotted?
Because he's not the base.
He's not cosecant. But if you can get the sign, how do you make it cosecant? Don't bounce yet. The first thing you should do is get your guidelines. And what are your guidelines? The tangents, cotangents, cosecants, and secants. The asymptotes. So how do I get asymptotes? Zeros. Reciprocal of 0 is undefined. Yeah. So reciprocal of 0 is going to be that guy. An asymptote. Going to be an asymptote. Going to be an asymptote. What's going to happen to all the maxes and mins? They're going to meet first, but yeah, you're right, they're going to bounce. As long as you make this guy look like the bounce of that guy, and this guy look like the bounce of that guy. Going from sine to cosecant is easy cheesy. Getting the sine can be hard. So getting the secant off of cosine should be easy cheesy. The cosine might be hard. Sophia.
What, like in real life problems, what do cosine or secant and
That's a good question. Secant and cosecant, this is just one example. There might be more just off the top of my head. I don't know. Cosecant and secant, there's this thing called polar graphing. That has to do kind of with like the latitudes and longitudes on our Earth are wrapped around a circle, and polar kind of helps with that, and graphing a different way. In polar curves, cosecants and secants are the way to get things like lines. Because polar graphing, everything's curved, and so to get anything linear, you need cosecants and secants. But that's a random example of where I've seen it used. Okay. So, in some ways, cosecants and secants are super easy, but in some ways, they're going to have more stuff going on than tangents and cotangents, because those waves have highest and lowest and have those 5 key points. So I know that the bell's about to ring. This would have just been a homework help, right? But what would you have graphed first? Cosine. So you would have thought about it as a cosine. So are you going to have to be practicing some of your section 4.5 skills? Alright, tackle homework. Thanks, guys. Chapel day, wish you could have gotten one more, but I think you got the idea. Let's come back tomorrow and see how you're doing. I'll be here after school if you need me. Sorry I wasn't here Friday.